We are in Unit 5, and this is our third section. So this is Notes 3. And in this section, we are looking at area and properties of definite integrals. Okay, so mainly properties of definite integrals, but also using area to evaluate a definite integral. Okay, so first of all, let's review what we know, what we learned from our last section. If f is continuous and non-negative, that means it's above the x-axis, non-negative, on the closed interval from a to b, then the area of the region bounded by the graph of f, the x-axis, and the lines x equals a and x equals b is equal to this integral. So again, definite integral, area under the curve. Okay, so usually when I show this picture and we're on day 2, a student will say, Miss Murray, what happens if the curve is below the x-axis? Okay, well, if the curve is below the x-axis, let's say we have this area, then this integral, the integral now from a to b of f of x dx, that would be the opposite, the negative of the area. Area is always positive, always, okay? So if the curve is below the x-axis, the integral will be a negative number. It'll be the negative value of the integral, of the area, okay? All right. So first of all, we're going to talk about some properties, and I should probably cover these up one at a time so we can do this all. Focus on one at a time here. Okay. I already talked about this last time, but when an integral has boundaries, it's called a definite integral, and if an integral does not have boundaries, it's called an indefinite integral. Okay. All right, we've already talked a bit about indefinite integrals. That's when we used the power rule. We talked about the power rule for integrals and stuff, the antiderivatives, and indefinite integrals and antiderivative. Okay, anyway. All right, properties of definite integrals. The first property is, what would happen if our integral was going from a number to itself? Well, if we're going from a to a, how much area is there? None. There's no area. So the integral from a number to itself of any function is 0. First property. Okay, next property. All right, so this integral from a to b is equal to opposite negative the integral from b to a. Okay, so every once in a while we will get an integral where we do something to get there. But let's say that we have an integral and we're going from like 6 to 2. Well, we don't really want to go from 6 to 2. We always want the lower number to be on the bottom. So what do we do to force it to be on the bottom? Well, we can move it to the bottom if we put a negative in front. Okay, so that's what this property is for. If you want to switch your boundaries, just put a negative in front of one of them. Okay, next property. All right, it looks a little bit like never mind, I'm not even going to say that. All right, if c is between a and b, then the integral from a to b is equal to the integral from a to c plus the integral from c to b. That makes sense. Let's say that we have that curve, and let's say that this is a over here, this is b over here, and let's say c is somewhere in between. It makes sense that the area of the entire thing is equal to the area from A to C plus the area from C to B. That's all it means. The the two areas will add up to the entire area, right? And again, there are some times when we need to do this or want to do this, depending on what the function is or for what our needs are in the problem. So this is one of the properties that is an obvious property, but sometimes it's a required property for us to use, okay? All right. This k is a constant, all right? So the integral of some constant times the function, dx, is equal to, we can pull that constant outside the integral, just like we could with a derivative. It works the same way. So we can take that constant and pull it outside the integral. That's a property. The integral of a sum or difference of functions is equal to the sum or difference of those integrals. And we've already kind of done that when we did the power rule. When we did the power rule and we had like an x cubed plus an x squared, we just took the integral of each piece and we were good using the power rule. Okay? So that's true. Now, what is not true, what kids want to be true, but it's not true, is what if this is a product? If this is a product or a quotient, the integral of a product is not equal to the product of the integrals. It's not equal to the product of the integrals. Same thing with a quotient. That is not equal to the quotient of the integrals. Okay? So, plus and minus? Yes. Multiply and divide? No. Don't do it. You're going to do it. And I'm going to say, nope, can't do it. And you're going to say, why not, Miss Murray? Because you can't. It just won't work. It won't work. It's not the same. The areas don't work that way. Okay? All right. Okay, if k is a constant, then the integral of the constant with respect to x is going to equal that constant times the difference, the delta x difference here, so b minus a. Okay? And we're going to see why that's true, but that's definitely true. And those are it. That's it. So those are our properties. These are not properties. Don't do those. Okay. All right. Examples. Okay. Let's start with this example. And this first example is actually property number 6. We're going to see why that's true. Okay. So example, sketch the graph and use a geometric formula to evaluate the integral. Okay, so this is the area under the curve y equals 6. So we're going to begin by graphing y equals 6. What does y equals 6 look like? Well, y equals 6 is a horizontal line up at y equals 6. It's a horizontal line up at y equals 6. We're going to find the area from x equals -4 to x equals 6. So we want to find this area right here. Well, this is a rectangle, isn't it? So this area is so this is a rectangle. And area is base times height. Okay. So our base is 10. Our height is 6. So our area is 60. It says to evaluate the integral. So for my answer, I'm going to come up here to my integral and say that is equal to, it's not approximately equal to anymore, it is equal to 60. Okay? let's look at this function. So again, by the way, this was the curve y equals 6. So we're graphing y equals f of x. Okay. So for the next one, we want to graph y equals x over 4, right? So I'm going to get some axes here. I know we're only going from x equals 0 to 8, so I'm not doing much on the negative x-axis, so it's all over here from 0 to 8. Okay? Well, this is a line. This is a line. The y-intercept is 0, right? And the slope is 1/4. So up 1 over 4, up 1 over 4. So up 1 over 4, up 1 over 4. And that will take us to 8, right? So there's my graph of y equals x over 4. We want to find the area underneath this curve from x equals 0 to x equals 8. So we're finding this area. Well, that is a triangle, right? That's a triangle. So, and the area of a triangle is 1/2 the base times the height. So our area will be 1/2. The base is 8. The height is 2 because we went up 1 over 2, up 1 over 4, up 1 over 4. So this will be 2 over here, right? So this will be 8. Our area will be 8. So evaluate the integral. Our integral equals 8. It is the area under that curve. Okay? The integral equals 8. All right. Next step. What does the graph of this look like? This is we need y equals square root 25 minus x squared. What does the graph of that look like? And if we were in class, we would spend a couple minutes and you guys would give me your ideas on what that graph looks like. But somebody would eventually say, Miss Murray, that is half of a circle. It is the top half of a circle. And it is. If you don't see that right off, put in 0 for x. If you put 0 in for x, you're up here at 5, right? Square root of 25, 5. Let me get a different color. If you put 5 in for x, you're over here at 0, right? If you put negative 5 in for x, you're also at 0. This is a semicircle, half of a circle. And so we want the integral from negative 5 to 5. Well, from negative 5 to 5 is right here. It is half of a circle. So our area of half a circle is 1/2 pi r squared. I need you to know what pi r squared is. Okay? So for us, our radius is 5. So our area is 25 pi over 2. So therefore our integral equals 25 pi over 2. Okay? You can always check a definite integral. Let's check this one right here. You can always check a definite integral. So remember Math 9. Math 9. Math 9 gets you to that integral. 0 to 8, x over 4, dx. 8. Okay? Every definite integral you can check on your calculator. Some calculators, not my calculator, but some calculators can check an indefinite integral as well. Those are awesome, but mine won't do that. For this one, it's going to be a little bit harder to see. Math 9, negative 5 to 5, square root 25 minus x squared with respect to x. It's working. Okay. It's hard to see that that's 25 pi over 2, right? But if we type in 25 pi over 2, we see that, oh, okay, it looks like they're the same after all. Does it show that they are the same? Almost. Almost. There's a little error here, right? The 25 pi over 2 is the exact answer, okay? That's exact answer. The calculator uses a numerical method to evaluate every definite integral. It uses a numerical method. And numerical methods have errors. Okay? So sometimes you can see the error and sometimes you cannot see the error. Sometimes the error is way back here, far enough out of our calculator's display. Okay? But there's always an error with a numerical method. So when you see, when your calculator spits out a definite integral value, know that that's close, but there might be an error there. Usually we don't care, okay? And it's always going to be accurate to 3 decimal places, so we're good in our course. All right, next up. Next up, example 4. Okay, for this example, we have got, they give us a graph of f of x. Okay, they give us a graph. And it's hard to see, but there is a little grid here. It's just hard to see. I wish that it was a little bit sharper, but anyway, that's okay. It's nice though when they give us a little grid. Okay. First off, we want to evaluate the definite integral from 0 to 3 of f of x dx. So remember, this is area, right? This is area. From 0 to 3, the entire curve is below the x-axis, is it not? So this integral will be the negative of this area. Area is always positive. An integral can be negative though, all right? So the integral can be negative. Area is always positive, okay? All right, so this area, it's a triangle. So 1/2 base times height. The base is 3. The height is 2. So that is the value of that definite integral, -3. Okay? Box your safe stop and then simplify, if you want to simplify. Yeah. I simplify only because we're going to be using that later in this problem. Okay? Next up, part B. Integral from -5 to 0. Well, from -5 to 0, the entire curve is above the x-axis. So this will just be the positive of the area. Just take the area. Okay? What I see here is I see a trapezoid. Okay? Hopefully you see a trapezoid too. But I see a trapezoid there, so I'm going to use my trapezoid area. It's the height times the sum of the bases. And remember, the bases are what the parallel sides are. The height is perpendicular to both bases. So the height here is 1, and the bases are 5 and 3. 5 and 3. So that turned out to be 4. Some people say, Miss Murray, can I split this apart? Of course you can split this apart. A lot of people say, okay, I don't want to use a trapezoid sum, or I don't want to find the area of that trapezoid. I would rather say, okay, I'm going to split this up. Each of these is 1, isn't it? Each of these has area 1 unit, square unit. Each of these is half of a square unit. So together they make a whole square unit. So that's 4. You can definitely do it that way. Okay? Definitely do it that way. All right, part C. In part C, we want the integral from 5 to negative 6. From 5 to negative 6. Okay, well that's a problem, you guys, because the first thing we need to do is always go from a lower number to a higher number. So I need to switch the negative 6 and the 5. And to switch the negative 6 and the 5, I need to make this a negative integral, because that's our property. We have to do that. So always be going from a lower number to a higher number here. Your b, what's on top, should always be greater than a, all right? It's always bigger than your bottom number. Okay. So now this is fine, we just have to keep that negative out front. And I'm finding the area from x equals negative 6 all the way over to x equals 5. So all these areas, okay? Well, this first little area is below the x-axis, is it not? So I need to make that first little area negative. And that's half of a unit, isn't it? Half of a square unit, so that's negative 1/2. Plus, my next piece is above the x-axis, and I just found it. It was 4. My next piece is below the x-axis, and I found that too. That was a negative 3. My last piece is also below the x-axis, so it's going to be negative as well. And that area is 1/2 the base times the height. So 1/2 2 times 1. Okay? So this turns out to be, that would be my safe stop spot. That would be my safe stop spot. Okay, this turns out to be a negative 1, right? That's a negative 1. So this is going to be 4 minus 4, so that's 0. So this whole thing turns out to be a half. Okay? Part D. The integral from negative 6 to 5 of the absolute value of x. What's the absolute value of f of x going to look like? Well, anything on f that's below the x-axis will be flipped up to be on top. So we will be taking all of these values, but they're all going to be positive. So this first little area would be a positive 1/2. The next part would stay a positive 4. The next piece would be a positive 3, and the last piece would be a positive 1. Safe stop. Safe stop. If you added that together, 8.5, 8.5, or 17/2. Okay. Part E. What do we do with that 4? Well, with that 4, we can just take it outside the integral and multiply it by the area of what we have left. Right? And we've already done this in part A. So this will be 4 times negative 3, which is negative 12. But this would be a safe stop spot. Okay? Now, part F, the 5, I could take outside, but before I even do that, look at our boundaries. I don't have to waste time taking the 5 outside because this whole thing is going to be 0. When your boundaries are the same, your integral is 0. Okay? Part G, let's split this up. Let's split this up. So for the first piece, this is going to be 2 times integral 0 to 3 of f of x dx. I'm splitting this up into its pieces. Plus, now I come to the 5, so the integral from 0 to 3 of 5 dx. Okay? So this is just 2 times negative 3, this we found in part A, plus, now we have the integral of 5 dx. Right? 5 dx. Do you remember back when Well, two things. When we were in example 1, we had the integral of 6 dx, and it ended up being 6 times 10. How did we get 10? B minus A, right? That was the distance, that's our base length. The 6 is our height. That's this property as well. 6 times 6 minus a negative 4, right? So here, when you have this integral of 5 dx from 0 to 3, it's 5 times 3 minus 0, or just 3. That would be a safe stop spot. This is negative 6 plus 15, or 9. Okay? Part H. No boundaries. No boundaries. I put this on here just to refresh your memory because this was back in our first section when we did the power rule for integrals. I put this on here just to remind ourselves so we didn't forget. If you don't have boundaries, then you're doing an indefinite integral, right? So we're using the power rule. Okay? So remember we added 1 to our exponent and then divided our coefficient by our new exponent. Add 1 to your exponent and then divide your coefficient by your new exponent. Add 1 to the exponent, so that'll make it an x to the first. Divide 7 by 1, you get 7, like that. And remember our constant of integration. So don't forget the power rule for integrals. That's finding the antiderivative. And remember, we can take the derivative of this to get back to that. If you take the derivative of 2x cubed, you get 6x squared. Derivative, negative 8x. Derivative, 7. Derivative, 0. Okay? All right. After our previous section, this one is refreshingly short. So hope you enjoyed it. So now you guys go try your hand on the homework problems.